Hi everyone, and welcome to the video lecture for Step 1, Skimming the Initial Datasets. In this video, we're going to explain how to take the nano AOD files, download them, and run the skimming code in order to pare them down to the data that is useful for our analysis, which is trying to look at the Higgs boson and its backgrounds in the tau-tau channel. Okay, so what we're going to do is make sure that we're all on the same page in terms of setting up our software. So the first thing I'm going to do is cd into my payload master area and then check that I've properly sourced the setup script. So I'm using a CVMFS mounted machine. So if I do something like root -lq and version, I should see version 6.16. If you don't see this version, go back to the setup instructions and follow them and make sure that we're all on the same page. So in my payload master area, I should see all these different files. And in the left, in the web browser, you see the commands that are necessary in order to execute the skimming. So I'm going to go through and execute those. First is to make a new directory. And then before we run the skim script, I'm going to open it up and let's read it together. What you see in this script is that there are two command line options for an input and output directory. And this is what we see in our web browser over here. There's two command line options, one of which looks kind of like a URL where we're downloading the files from, and the other is our local directory where we're going to store the output files. Then we see that we're going to be compiling an executable. So on this line, we're using our compiler to compile this skim.cxx file into some output executable called skim. Then once we have our executable, we're going to read a sample and a cross section from skim.csv into our input file stream. And then we're going to execute the skim script on every sample. So for every sample present in skim.csv, this script will compile and run the code in skim.cxx on that sample. So this makes sense. This on a high level agrees with what we expect to be doing in this stage of the analysis. So let's open up skim.csv. So we see the familiar names of our signal samples like glue glue H to tau tau and VBF H to tau tau, so Higgs decaying to tau tau. We also see backgrounds like Trelian, TT bar, and various W backgrounds. And then the final two lines we see are data samples. So I'm going to do something a little bit different here. I'm going to trim this file down to just be the two data samples. So I don't want you guys to do this, but this will allow me to demo this code on the fly, and it will take much longer if I don't trim down skim.csv. So like we said, we need to download the files and then run over them. And this can be broken up into two different steps if you wish. So there's this download.sh script reference in the second block of bash script in your web browser. So I'm going to make the relevant directory for that. And then let's look at what's in download.sh. It's got a somewhat familiar structure with an input file stream reading a sample from skim.csv. And it's just going to execute a command to download the file to the output directory. So I'm going to run download.sh first just to show you how it works. So I've come back with an error because I've already downloaded these samples before, and that's fine. I'll just remove them. And then I'll try again. So I'm seeing output this time. It looks like I've downloaded them. And out of curiosity, let's open one of them up in root and let's see what it looks like. So I'll do root-l and I'll run on the glue sample. So I've got our gluon fusion sample. I'm loading it into root, and you see it should be attached as file 0. So if I take file 0 and ls it, I see that there's a T tree in this file called events. Now, what is events? We can take it and print it, and we see a whole bunch of output. There's 68 different branches in this T tree. If we scroll up to the top, we see information like the run number, the event number, which is interesting, but not necessary to this analysis. And if we scroll down, we see things like the number of muons, and then variables like muon PT, so a lot of kinematic variables that are indexed by the number of muons. And if we scroll down some more, we see branch 26 is the number of taus, and again, things like tau PT are indexed by the number of taus. So this file potentially for every event has multiple taus and or multiple muons, depending on what was going on in that event. And we're saving the kinematic variables for all of the muons and taus. Now, really, we're interested in some sort of leading or subleading pair of muons or taus that are same sign or opposite sign in order to do our physics. So there's probably a lot that we're keeping around that we don't need, hence why we're doing skimming. So now let's actually run the skimming script. I'm going to run it from these samples I've downloaded since I already have them locally. You can just run them over the first script that runs it from the network if that's what you wish to do. Either way is totally fine. So you can see that as I type, I'm referencing my input directory to be what I've downloaded, and then my output directory is the one I made for my skims. You can see it's going to be compiling the skimming executable, and this will take just a moment, and then it will run over the 2 samples that I've defined. I want to make sure that all of you are running over all of the samples in order to do the full analysis. That will take maybe 10 to 15 minutes. So this is another reason why I've trimmed down my skim.csv, is it allows me to demo this script on the fly. You can see some of the output, but you don't have to wait around 15 minutes for all of it to run. And you can see some hints of skimming. Print out like event has good taus, 1,000 pass out of 4,900, so a 21% efficiency. So you can see that there's some good output telling you that this is indeed doing some kind of skimming. Now, let us look at the output file. So I'm going to again do root-l, and this time I'm going to point it to skims, and again to our glue h to tau tau. The file has again been attached as file 0. So let's take that and see what's present in this root file. Well, it's a T tree of events, okay? But this time it's a little bit different of a tree. So we see right off the bat that we only have 36 branches rather than 68. And if we scroll up to the top, we see that information like run number and event number has been cut out. And we've kept some kinematic variables like PT, eta, phi, and then if we scroll down a little bit more, PT2, eta2, phi2. And so what this means is that in this skimmed version, we've decided which pair of physics objects is our most interesting, and we've only kept the kinematic information for that pair of objects. So maybe this is a tau pair, a muon pair, or some other pair of physics objects. And we've decided that these are the leading and subleading objects we're interested in, so we're only going to keep the information for these two objects. We no longer have branches that are indexed. Each branch is just a number now. So that's pretty good. This is another strong piece of evidence that we've actually skimmed down these files. But let's see, if we really skim them, the file size itself should have been reduced by quite a bit. So I'm going to do ls with the -lhrt commands. This will just produce human readable output for the file size. And let's look at the difference between home, awesome workshop, samples, the glue file. So the downloaded sample was 20 megabytes. And now let's do the same, but for skims. I forgot the naming convention. We put the word skim at the end of the file name now. Okay, so comparing, we see 20 megabytes for our sample that we downloaded, but only 85 kilobytes for the sample that we've skimmed. So clearly, the file size is being reduced. We're throwing out a lot of stuff. Now, as the last step here, let's actually unpack skim.cxx, look inside, and see what's going on. So you open it up, you might be a little bit intimidated if you're not super fluent in C++ with things like templates and auto. But let's scroll down to find some human readable main method. And we found it here at the end. We see that we're going to make a root data frame, something called events. So we're probably making it from our T tree called events. And then we're going to apply several of these user-defined functions iteratively on our data frame. So each of these functions is going to be performing some high-level task, like finding good muons, finding good taus, finding the muon-tau pair, and so on. So this makes sense. There's a series of filters that we need to put our events through to see if they pass, if they have the right physics objects, and then we just save the file to some new output file. So let's look at one of these things like find good muons. We take our data frame, we define some new variable, good muons. And these are muons with the following characteristics. They have an eta cut, they have a PT cut, and they have some trigger ID. And this is the case if you scroll through and read all of these methods. So in actuality, this code is relatively straightforward, and it's just taking a data frame that's created from our T tree, maybe defining some new variables, maybe cutting out events. If it, for instance, minimal selection, if it doesn't have any muons or taus, it's really not interesting to us, so we're going to filter it out. Okay, and so that's all I have for you in the skimming step today. I'd like you to run this and then join us in the next video. And between now and then, I'm going to rerun the full skimming offline because it takes, like I said, about 15 minutes. And so I will have all of my skim samples in the next video when we meet up back together. All right, so thank you for watching, and I'll see you in the next video.